So what we've talked about so far, I guess in the class, I got it next, yeah, is have really been, if I roll this up a little bit, just to draw on this, what we've really been talking about so far is the idea that if we have some kind of spill, we have some, I use my artistic license in all of this. If you had little lenses of lower permeability material that sits in here, and I suppose I'll make my life easy by drawing myself a water table, so that almost this is in the saturated zone. And so what we have talked about so far is being able to understand a couple of things about this. We'd like to know what the saturation profiles would be as a function of depth, say. We'd like to know something about how relative permeabilities might vary as a function of depth and as a function of maybe saturation of water or the non-wetting component. And we've used that to say, to get some very simple models of if we have flow through here at some velocity and therefore volumetric flow rate, we can do some interesting calculations as to what the loading would be downstream in terms of concentration. And so at some compliance point downstream, wherever that might be, you're sucking water out of here, such as in your very first assignment, if you're sucking water out of the aquifer, then you might like to know as to what the residence time distribution would be at that point, and you've done these calculations already to say something like concentration changes with time, and it does something. It arrives at some time, and that's useful to know. And so the other thing that we might be interested to know is what does this distribution look like? Is it vertical? Is it angled? Is it much flatter? So we'd be interested to know what this time is when this happens, and you've done some simple calculations to do that from basically the observation that advective velocity is just equal to length traveled over time taken, which obviously gives you, not obviously, but gives you a direct plug flow, plug arrival. But that's not necessarily really the case. And so we'd like to know what's the arrival time. We'd like to know what does this ramp up in the concentration look like. Is it sudden or is it more gradual? We'd also like to know, I suppose, whether when it arrives, it really arrives at the concentration that we think it is from the upstream, which we've called the solubility limit before, right? We've defined the solubility of these components. It's 1100 parts per million or 1100 milligrams per liter for TCE. And that's the maximum amount that can be held in water at equilibrium. Can't get more than that, could be less than that. And we've assumed that that would be the loading that would be carried downstream. And so in our idealized look at this, I suppose the only tool that we've had is that the residence time distribution physically does look like this. It has a sharp front of arrival. It arrives at exactly the arrival time which is given by this expression here. And that when it arrives at the maximum concentration, which is this solubility limit. Whoops. And so that's been good enough for us for now. I guess what we'd like to do now is examine whether those are really adequate descriptions of what's going to happen. And so that's really what our task is. And so I want to very distinctly make the case. Sometimes I think it's confusing, maybe in the assignments, but we're very distinctly making the case that instead of looking at the transport of these components as free phase to get into the position where they're held in place by capillary forces, and if we want to remove them, we can remove them by dissolving them, but typically most of the flow in this would be water. To note the fact that if we're looking at this system, now what we're interested in saying something about is that we can represent the behavior as being a source region, if we like. So I'm trying to represent this whole thing here. This is our source. And if we have some low permeability stratum underneath it, then we'd expect that over time, this plume, if you like, would develop like this. So that at time T1 it would be here, at a later time T2 it would be here, at T3 it would be somewhere further, and so on. And so what we'd like to do is now look at how this stuff gets dissolved in the water from this source region and gets carried downstream, so that now if we tap this and remove some fluid from here, we can also find out what the concentration as a function of time would be, which is really what this is, right? We'd like to be able to figure out exactly what that is. So that's our task. So do remember that we're talking about not free phase transport anymore, not being driven by relative permeability. What relative permeabilities tell us is they tell us something about the flow rates of the velocity of the fluid, the so-called advective velocity, but we have to use that advective velocity of the fluid to be able to create these plots. And so that's our task. And so one very simple conceptualization we'll use is we'll think of this aquifer, instead of being an aquifer, one very easy conceptualization is just to think of it as a kind of a hydraulic conductivity test where you take a tube, you fill the tube up with your aquifer, and you have water flowing down your aquifer at some advective velocity. You look at the concentrations at this downstream compliance point, if you like. In other words, this kind of behavior at this compliance point as a function of applying some source upstream. So this also is the source. And in this particular geometry, this plume would look like it would be somewhere at time T1, it would somewhere further at time T2, and it'd be somewhere further at time T3. If these were, if you like, these are pictures of the front, which has to be defined as some threshold concentration in water. So that's what we're going to try and do. That's our attempt. So it is important to realize that we're talking about no longer material that is being moved as a free, independent, immiscible fluid, but one now which is dissolved in water, and we're only interested in the rate at which water flows through the system. So it's exactly the same as your assignment number 4 that you're basically doing now. Okay. Oops. Okay. So this is what we'd like to talk about. So I guess hopefully we set the stage. So we'll talk about the mechanisms by which transport occurs. There are really two. The first is called dispersion, and or two mechanisms that both look the same. One is molecular diffusion, and one is mechanical mixing by dispersion. And the second one is by being carried by the bulk motion of the fluid, such as you've done in some of your calculations so far. The calculation that velocity is equal to length traveled divided by time. And in the absence of dispersion or diffusion, and also in the absence of retardation, very good. That's even better than seeing people crack their knuckles, crack their necks. Retardation and attenuation. But I digress. And so you could imagine that this is the observation of what happens. The plume gets attenuated. The mechanism, I suppose, is by sorption. And so you could imagine that if you sorb a certain amount of the contaminant onto the solid substrate, on the grains of the soil, then it's no longer in the water, and so you think that you reduce the concentration. And so both of these effects, diffusion and dispersion, to spread it out, and retardation and attenuation to remove it from the water and therefore lessen the concentration, will stop it from looking like what would otherwise just be plug flow. And so the plug flow would be just the stuff that you've been talking about before. If this is time versus concentration, then this really would be the upstream source concentration, this really would be the arrival time, and this really would be absolutely sharp. Only if both of these things are zero, and also if this is zero. If they're non-zero, then it won't conform to that. And so our first discussion about this is to talk about what we will call conservative transport. It's not a political statement in terms of liberal versus conservative, but it's merely making a statement that mass is conserved. All the mass that starts off in the fluid remains in the fluid as it goes from upstream to downstream. None of it is sorbed onto the grains, and therefore you'd expect to get the highest concentrations downstream fastest in that particular mode. If it's non-conservative, it means it's sorbed partly, and as a result will end up as a lower concentration downstream. So certainly for today, in the next couple of times, we'll talk only about what we call conservative transport. So this is this. So this is the best picture, I think, to be able to make the case for what we're talking about. We've talked about these two mechanisms. First is advection, which is really what we've discussed in terms of the velocity it travels downstream at is the advective velocity. And you remember that the advective velocity is equal to the Darcy velocity divided by porosity. Or if it's unsaturated, we can also write it as equal to the Darcy velocity divided by the volumetric moisture content. The pore space might not be 100% filled with water, for instance, and this is only transport typically within the water. And in this we know that the Darcy velocity is just given by Darcy's law. So the velocity is hydraulic conductivity. I suppose it could be multiplied by relative conductivity at that particular volumetric moisture content, and the gradient of head with length. So this is just Darcy's law. And so that's advection would give us this step change in concentration. And so the way to think about both of these terms together is that there's a second behavior in conservative transport. So these are all conservative. Mechanisms. And that is this diffusion and mechanical dispersion behavior. And so for me, the easiest way to describe that, I think, is to think about taking a beaker that's filled with water, and you drop an ink drop into that. I don't know if it sits on the surface. So this is the ink drop that you drop in. That's a very big drop of ink. Ink is typically, I guess, it's probably a trace amount of ink pigment, and it's probably 99% water, I'd imagine, but I don't know what the proportions are. And so once you put this in the a beaker, you'd know that what you'd expect to happen is that this little thing would slowly diffuse out by Brownian motion. And so it happens to be in a beaker. It's only water. It's like being in a swimming pool. And if you took a cross section across here from one side to the other, then and drew out the concentration as a function of time, then it would look something like this. Initially, when you put it in, it looks like Manhattan. If you look a little while later, it'll look a little less like Manhattan. It'll look like the Catskills. And then you look a little while later, it should be centered on here, and it will be Iowa, maybe, or something. And so it's basically a behavior where you can think of it as being driven by something you know. You know that mass flux, according to Fick's law, is given by a diffusion coefficient multiplied by a change in concentration with length. I guess it's called x. Then this would be x here, and this would be the profile of concentration. And so if you think about it, and I've not drawn this very well, I guess I could make it bigger, and then I might be able to draw it. If you think about it, then this component here, this little triangle, is exactly the change in concentration with the change in length. It's exactly this term here. And so really Fick's law is saying that nature really dislikes these infinite gradients, and it tries to get rid of them by dispersing them, and it does it by the mechanism called diffusion. And that diffusion takes this infinite initial gradient, and after time, this is time t0, this is time 1, this is time 2. It basically gets rid of it by reducing trying to get the gradient down to 0, where everything's the same. And that's what's going on. And so that's what happens in an aquifer. It doesn't matter whether we're talking about, thinking about it in terms of a beaker, which has no sand in it, or if you fill the beaker up with sand after you put the water in and then put the ink in it, it's the same behavior. It's just now that it's moving within this kind of tortuous space. And so you can think of diffusion as basically that process where you look at the behavior going from, which I've drawn on its side here, by Manhattan at time t0 and then flattening out as time goes on. And so that's something that physically happens in space. What you could do is, instead of doing that, what you could also do, so I guess I could rotate this around, right? You see, this is the, where's it go? This is it here. So this basically, this behavior here is exactly what we just drew. And so what you could do is you can think about the confluence, if you like, between these. I'm trying to get it back. Yeah. The confluence between these two mechanisms of advection on one hand and diffusion and dispersion at the other hand is that if you take the beaker and I physically move it across the room to another location, then that's taking diffusion, which is occurring in the beaker over time, and I'm physically choosing to move that to another location. And so if you look at the processes in groundwater aquifers, it's basically that. You could think of taking this ink drop, which is in your beaker at time t0, which looks at Manhattan, and if you leave it static in the beaker, over time it will change to look like this secondary, more spread out distribution. And that's happening only as a function of time. Nothing else has to intercede to do that. But you could also have the water that's in the beaker, think of the beaker moving through the porous medium, and if you look at the beaker after some later time, after which it's traveled some extra distance, all of a sudden, if you look at the distribution of the concentration in the beaker, it doesn't look like it did before. It looks like this. And so that's exactly what mechanical dispersion is. And so as you go downstream, then it spreads out, because the two particles of ink that started off here, one goes on one pathway, the other goes on another pathway. And so if you look at where they are at arrival, all of a sudden it looks different. And so the reason that diffusion, which is molecular random walk, Brownian motion is a random walk, which occurs without this mechanical agitation, and mechanical dispersion are both lumped together as a single property, is because they look identical. If you don't know what the reference frame is, and you look at the beaker at time 1 and time 2, and you don't realize that the beaker has physically moved downstream, then you wouldn't know what's going on. Good luck. And so that's what it is. And so they're two physically different mechanisms. They're lumped together because they just look identical to an observer. If you're an observer upstream and downstream, that goes from upstream to downstream, then you see that the distribution is like this red line after some time, and it looks identical to the behavior of the diffusion. And so that's why we use it. So it turns out that we can think of mechanical dispersion and represent it like by a diffusion-like process, which is Fick's law, which causes this behavior, even though it's nothing to do with it. So that's the rub. So to recap, two mechanisms. Being carried downstream without any mixing is advection. But if we look at the effects that we get mixing due to two processes, one is due to molecular diffusion, that it gets rid of these gradients by just Brownian motion, and also by physical mixing as it gets agitated as it goes downstream. And all we're doing is we're taking a section at two locations and being able to link those together. Okay? So that's, I think, an important concept in this. So what we'll do is we'll take each of these two components together. The first one will be the diffusive behavior, dispersive diffusive behavior, and the second one will be advection. And we'll talk about how we put together some equations that define what's going on. I'm not particularly worried about your understanding these equations in this class from the PDEs anyway, but it's useful to kind of understand where they're coming from. And probably what we've talked about already is enough. Diffusion as a process is basically getting rid of a concentration gradient. It's the same as what we call Brownian motion, kind of random walk of molecules. And I guess if you look at it in a thermodynamic way, if you can cast your minds back to thermo, you're basically increasing entropy in a system, making more disorder. You're going from a concentrated location to dispersing it all over the place. Much more difficult to clean out. You can imagine if you wanted to suck up the ink spot straight away with a straw, it'd be much easier than once it's disseminated itself throughout all the water. We can think about it occurring in stagnant fluid. It follows Fick's law. And what we typically do is we take Fick's law and we can write it as a conservation of mass. Not now of the water that's traveling, but a conservation of mass of dissolved component in the water. And so if you look at the concentration of mass within the water, if you look at the porosity of your aquifer, and if you look at the mass fluxes of that particular component, whether it's gold dissolved in water or it's TC dissolved in water, it's the mass of that particular compound traveling per unit time, then this is just a conservation equation. This basically says that mass in minus mass out into a control volume equals accumulation. So if you wondered why we talk about these things in fluid mechanics, this is the basis of all hydrology and mass transport. So you have a bucket, the amount going into the bucket minus the amount going out of the bucket has to be the amount that accumulates. And this is just the way to write it in a differential way, when that bucket, instead of being a bucket, is just a little differential cube where stuff is going in from the upstream, I guess, right-hand coordinate system, maybe happy or unhappy memories, I'm not sure. X, Y, and Z. And this would just be the flux in the Y direction, through the face. So don't need to know anything more than that. So what we can do is, if you realize, you could take this flux, which in this case would be a flux in the x direction, we could throw it into this expression here. If we do that and manipulate things, we end up with a partial differential equation, which is the so-called diffusion equation. The diffusion of a mass through a porous medium. And it has a parameter in it. This is diffusion coefficient. I guess it's written here. It's in units of meters squared over time. And concentrations are in mass per unit volume. Typically C is in terms of mass per length cubed. That's my expression to talk about the equivalent units, which we've used before. And so that's the diffusion equation. And it's not so important for us to solve these equations, but to realize what it means. The one thing I guess that we should back up and say something about is that we talked before about doing this for a beaker which was filled with water, in which case the diffusion coefficient would be the value of the diffusion coefficient for that compound in water on its own. If you fill that beaker up with soil, with sand, say, then you can imagine that instead of being in the beaker where this plume just spreads out directly in the water like this, then if it has to go in and out of the pore space, you could imagine taking this Gaussian distribution and wriggling it through the pore space, which is what this little diagram here is. So if you imagine these little black things as being grains of sand, and the pore space would be between them, then presumably you could draw the base of this diagram here as a flow line, which would go between these little grains of sand, right? Oh, a heart. This looks like a heart. It's Valentine's Day, of course, coming up. So if you think about this pathway through here as being this axis here, x, wrapped along that direction, which is what this is saying, then you could imagine this Gaussian distribution being this crenulated thing that goes along. And so you'd imagine that it's really no different. It's just that now the flow path is actually, in going from here to Altoona, it's not as the crow flies anymore, but it's having to go along the roads to get there. And so the effective length to get there would be longer. It's tortuous. And so you could imagine that if you have to make the stuff flow along this tortuous flow path, then the diffusion coefficient, which is the diffusion coefficient that you need here, is going to be different from it would be if it was just in water. And that indeed is the case. That's what we're making the case for. And that is, if we look at this flow through a porous medium, we have to use an effective diffusion coefficient. And we can get this effective diffusion coefficient by taking the one that you'd look up in a reference book for the diffusion of sodium chloride in water, which would be a number like 10 to the minus 9 meters per second, something of that order. I wouldn't be surprised. It would be typically of the order of 10 to the minus 9 meters squared per second, something like that, for lots of different compounds. But you have to modify it by some number to account for the fact that it's flowing on this tortuous flow path. And numbers for this effect of tortuosity might reduce its effective magnitude by half or to 100th, something in there. And you could test to do that if you want to. But you could imagine that because it's going to have to travel further to get from A to B as the crow flies, that it would take longer to do it because it's traveling on a longer path. And that's really what you'd expect. And so what we could do is we could rewrite our effective diffusion equation not as for behavior in an ideal material, but one where it's modified to account for the fact that it flows along a more tortuous path. Bless you. And if we do that, then we end up with this. Don't really care about trying to solve this or trying to solve the equation, but to note that there are some standard results. we've already stumbled across one of them, I guess, originally. I tried using my WX Maxima, which is Mathematica, and it didn't work, so I'm not going to go back to that. If you want to look at last year's video, 2 years ago video, then it's in there. But we could just not solve this equation, we could actually calculate this equation on your calculator. And it turns out that if you look at the solution for this equation, when all of a sudden at point 0 in your beaker, I'm going to push this up a little bit. So if you look at point 0 in a beaker, all of a sudden you put a concentration of something at time 0 that goes up to some magnitude 1. In other words, this would be Manhattan at this point, if I can keep on going up. This would be the concentration at time 0. And you basically turn it on right there. Then the distribution of this ink as you go out from the center of this beaker is this curve here. And this curve is given by this equation. Complementary error function, you don't need to know how to figure it on a calculator. We've used it in assignments and tests given it as a standard result. But it basically says that the behavior of this concentration profile will always look like this. It's exactly the same as a Gaussian distribution, standard probability bell curve. And it allows you to say something about the distribution of that concentration, which is really just redrawing what we talked about before. Manhattan turning into progressively this, and getting flatter as time goes on. This should be highest in this point here, right? Where the units of here are relative concentration. If it's relative concentration, the maximum is always 1. And it would spread out from there. This is always the length of direction. And I suppose if you remember your statistics, I don't like statistics very much. I always like Ernest Rutherford's comment on statistics. Statistics obviously is useful, but his comment on statistics was if you need statistics to interpret your experiment, do another experiment or a better experiment. So basically, he's working in places where he could control the boundary conditions quite well. So, but geostatistics and other things certainly have a role. So I'm trying to think about statistics. What is this? This is something like, so if this is a distance here, this means that, what is this? This is 3 standard deviations, right? 3 sigma. If this contains, what is it, 99.6%. So in other words, if 99.6% of the mass exists within the limits of this boundary here, I won't color it in, then that that is defined by 3 standard deviations. So so this is no different from a bell curve that describes this behavior. So it's just the spreading behavior. And so it's a standard result that we can use to be able to look at what this plume would look like as you allow it to spread. So we know how to quantify this both within a beaker, when the equation that we solve would have this just as what we call d sub d, which would be the diffusion coefficient. And if the beaker is filled with sand and we have an effective diffusion coefficient, then it will just respond to a different value of this parameter. But either way we can calculate it. And it will look the same in either case, but in one case it will just take longer to get there. That's all. And this is a cumulative distribution here. Right? So that is one realization of this. We will use this to do 2 things. We'll use this to represent, first of all, diffusion. Which seems pretty a logical extension from what we talked about, right? It's a diffusive process through what we're representing, and so it should look like diffusion. But we'll also use the same mechanism to represent mechanical dispersion. dispersion. And the reason that we'll do this is, or the reason we're able to do this, is just going back to the fact of what we said here. If you look at the behaviors that you get from mechanical dispersion, it looks exactly the same as diffusion. It's just separated by some physical location where you're taking those measurements. It's like taking a beaker, putting sand in it, dropping, or not putting sand in it, putting a drop of ink in it, and then walking across the room to the other side, and then looking at what that distribution of concentration looks like. It's physically moved across the room, and it's diffused in that case by diffusion only. But if in going across the other side of the room it was mixed by mechanical mixing, then it would be exactly the same as the process we're talking about. And I guess what we're saying is that this diffusion equation that we talked about here can represent both diffusion and a process that looks exactly the same as it, albeit the fact that the coefficient that controls it will be something different. That's what we're saying. Okay? All right, so the two processes we talked about. The first was diffusion and by inference mechanical dispersion. The second was advection, which is physically traveling across space. We know that advective velocities are given by this expression here, right? This is just Darcy's law. So this is actually the same as just Darcy's law, Darcy velocity divided by porosity, this term here. Nothing more than that. And so this allows us, for instance, to be able to find out exactly what the rate of flow of water, only water, not of the free product, because it's immobile, not of the dissolved constituent, but the water travels at. If we know the rate at that water is traveling, then we can calculate the mass flux. The mass flux would be the Darcy velocity. So in other words, look at this expression here. Well, let's just come back to that in a second. The mass flux is going to be the Darcy velocity multiplied by the concentration. You're using that in your current assignment, right? The velocity, the Darcy velocity multiplied by the concentration gives you the mass flux per unit area. If you multiplied the mass flux per unit area multiplied by an area, you'd end up with this would now be what we've called Q, and this would be, I think we've called it m dot, right? Mass flux. So this is the contaminant mass flux. Volumetric flow rate by concentration gives that. That's the expression we used last time. Volumetric concentration is just the product of Darcy velocity and area. Darcy velocity is concentration, is the advective velocity times porosity, just from this expression here. And so it should be all copacetic. So this would be kilograms per unit time per meter squared, I think. Should be able to show what this is here. If concentration is in units of kilograms per meter cubed, if velocity is in terms of meters per second, I guess I meant to write that. Didn't mean to write it there. Velocity is in meters per second. Then if you take the product of these two, then you should get kilograms per meter squared second, which is this. Anyway, it doesn't matter, just playing around with the units. But anyway, so if we know what this flux is, and we put it in exactly the same conservation equation, mass in minus mass out, equals accumulation, exactly before. And do some substitutions, well, we end up with this final expression here. It doesn't particularly matter all that much about this, but it also is the same equation as before. The left-hand side is a rate at which you're accumulating contaminant in that bucket, control volume, differential cube, whatever you want to think of it. And this is the rate at which it's going in one side and coming out the other side, the difference between those two rates. It's driven by an advective flux. It's driven by a concentration gradient in the bucket, and that's all we need to know. And so our reason for doing that is that what we can do now is we could put these two together. And so we could look at, for instance, the influence of advection, which is shown here. We could look at the influence, I'm going to scroll up, but I'll come back. We can look at the influence of diffusion. And we could take those two effects and add them together. And I don't particularly care about this expression, only to make the point that if we look at the Advection-diffusion equation, it would look something like this. Change in concentration with time. In other words, the left-hand side from both of these equations, and I'm going to write just three terms, is equal to the diffusive part, which we call d star, multiplied by the change in concentration with space, and minus this expression here, the advective velocity multiplied by the change in concentration with space. So, just so it's in one place. So this really is now representing the flow in our little tube, our cylinder of soil. And if we think of it in that way, we can think of this in terms of just three components. This is an accumulation term. This is a term that represents diffusion, spreading, if you like, by diffusion. And this is a term that represents lateral, longitudinal extension by advection. So these three components come together. And so what we could do is we could take this behavior of a tube that we've talked about. So in other words, if we think about just a little tube that we have, that we're going to do something to the upstream part to in terms of a source, and then we could look at what we'd expect the behaviors to look like. And so we're just going to do it in a descriptive way to be able to make sure that everyone kind of understands what to expect. So you could think about the boundary condition that you apply to this upstream portion. So think about this being a trough that has water in it, and into this water we're going to put some ink or something else. And so what we're going to do is at time t0, all of a sudden in this trough upstream, we're going to change the concentration from being 0 to being 1. We turn it on instantly. So this is the rate, the change that occurs in this upstream reservoir that we'll call R. So what would we expect to happen if we look along the length of this at a particular snapshot in time? If we don't think there's any diffusion occurring, then I suppose we'd expect that after some amount of time, the plume would have gone some distance, maybe to here, and it would have gone this length, just as we've drawn in this lower plot. And this length that it's traveled is equal to the product of the advective velocity multiplied by the time since we introduced it. So this would be just time. I guess previously we called it t, the arrival time, right? Although it's not really arriving, it's arriving at this point. And so if we looked at what the concentration looked like along the length of this tube, then everything upstream of this one point would have reached the background concentration of the reservoir. Everything ahead of it would not have seen it yet because it hasn't got there. And so this red profile would be the case, for instance, when D star is equal to 0. Not very well done. This is D star. And so this is saying that this diffusion coefficient doesn't happen. It doesn't allow any spreading. And so if you think about what this would look like, even as the beaker goes across the classroom, it always stays looking like Manhattan. It always stays this vertical profile. Never diffuses. And the equivalent for that is you keep on supplying it from upstream, is that it would give you this distribution, which should be, as you know, as plug flow. It's called plug flow. If you allow this diffusion coefficient to increase, what it does, it would follow one of these green curves. And the most obvious example is the larger diffusion. So the diffusion for this green one would be larger than the diffusion for this one. This one's 0, this is 1, this is 2, whatever numbers you want to put on it. And so I guess the implications for that would be that if you are sitting in this aquifer at this particular point here, and the diffusion coefficient was this amount, well, even though the advective pulse really hasn't arrived with you yet, you'd be seeing some concentration which is larger than the concentration that you should see, because it's already got there and it shouldn't have done. And so I suppose the explanation of that is if you draw a cartoon to represent flow along this tube, would be that you might be able to imagine some pathways in here that maybe had higher permeability, and therefore the fluid was traveling faster than the average fluid. So if you had some of these stringers. So that if you look at where the front might have got to, these little fingers of the contaminant might have actually reached further along in some places. I can't lift up my pen because it has a problem. I don't know whether this looks coherent to you or just like a scribble. But if you look at any point across the aquifer here, this would be 100% concentration, this would be 100% concentration, this would be 0% concentration. If you take the average across this thing, then you have some 20% concentration. And so that's physically what it's representing. Likewise, if you looked at this point back here, haven't drawn it very well, some of it would still be water, some of it would, because of these things lying back here maybe, like this one here, some of them would be 100% concentrated, and so this concentration would be maybe 80-20. Whereas this one here is 15-85. And that's really what this physically is saying. Nothing more than that. And so this is the mechanism by which it occurs. And that's really what it is. So that's really what you need to know about the advection-diffusion equation. This term here says something about the rate at which this front will arrive. And it's not a bad approximation for now for us to assume that this expression gives us it exactly. It isn't true, but for now, let's not worry about that. We'll disabuse you of that later. So that gives you the arrival, how quickly the beaker arrives downstream across the classroom. And the second part is the dispersion part, diffusion part. If this is 0, it'll be plug flow. If it's non-zero, it'll be progressively cant further and further over until it's very flat. Okay. We could think of this where you dump stuff into the ground and you leave it there, and it's there to dissolve over a very long period of time because the rate at which you're removing it is very small, just like the example you're doing in assignment 4. Or it could be a plug that's put in maybe as an aqueous component. Maybe you put a mixture of gold dissolved in water into the ground, or iron dissolved in water like you would with acid mine drainage, and it's not coating the particles as a continuing source that gets renewed as you flush it out. And if that's the case, then you could think about throwing sodium chloride solution into here, that the reservoir is very small, and then after you've put in your sodium chloride solution, you then flush it, keep on flushing it with straight water. So that would represent the case where you injected a dilute solution of something in the ground and then kept on injecting water afterwards. You'd get the similar behavior, except the plume that goes downstream would basically look like taking a beaker that has it in as a central source at time 0, moving the beaker downstream, and so that when you get across the other side of the room, it's no longer Manhattan, but it's spread out. And so that's exactly the behavior you'd expect to see for that particular boundary condition, just a different boundary condition. It's a spike that you inject, and then you inject water afterwards at this upstream location. If there's no dispersion, then you'd expect it to look at a concentration of one just translating down the aquifer until it gets to the outlet at this point. If there is dispersion, so this is D equals 0, D star equals 0, and this would be D equals 1, as we said before, and 2, just different numbers. So that's it. So that's what you need to understand. They differ because they're at the same average location because the advective velocities are the same. They differ in the degree at which they're canted over because the magnitude of the diffusion coefficient is changing. And they differ absolutely in terms of shape. One's a step function, one's a delta function. They differ in terms of shape because the boundary conditions that created them are different. And so that's really what we need to understand about this to be able to go ahead. Okay, so that's an important component. So what we will do is we'll develop some expressions, or use some expressions to recreate what exactly these pulses look like in a quantitative way, not just a descriptive way. But understanding in a descriptive way, I guess, is the best precursor to make sure that you'll be able to use those expressions successfully. Okay. Hope I'm not belaboring the point. I never get much feedback as to whether I'm belaboring it or going too fast or slow, etc. So, how's it going? All right. Well, we'll plow ahead then. Let's plow ahead. Okay. So we talked about each of these: diffusion and advection. We talked about dispersion being diffusion-like. So let's talk about what the mechanisms by which that occur are: mechanical dispersion and hydrodynamic dispersion. So, whoops. So these are the key understandings. So there are a number of mechanisms by which you could imagine this could occur. We've explained kind of how it happens before. It could occur by the fact that we have a distribution of particle sizes and therefore pore throat sizes. We know, for instance, that permeability is proportional to diameter squared, right? Diameter of the particles or diameter of the pore spaces. So if you have very small pore spaces, the permeability will be very low, and therefore, since we know that advective velocity is equal to hydraulic conductivity, let's not do that. Permeability over viscosity times change in pressure, just our other way of writing Darcy's law. If permeability is low, then advective velocity will be low. Permeability is high, it'd be high. And so if you have pathways through small pore throats, it'll be relatively slow moving. If it's going through fast pore throats, so if you start the races with a particle here at time t0 and look where it is 10 minutes later, if it's going slowly, it'll have gone half as far as a particle that's traveling twice as fast. And so you'd expect to get a distribution of two different fronts that have been separated as it goes through it. If you have tortuous behavior that takes different paths, as we said before, even in a uniformly graded bead pack, you'd end up with different random pathways through that bead pack. And so you'd get spreading from a point here to a point downstream that would look like this Gaussian distribution, as we made the point for before, even in a perfectly homogeneous material, if that exists. And the third effect that we can think about is something called Taylor dispersion. And Taylor dispersion is basically the idea that if you take a pore throat and you think of that pore throat as being a capillary tube, then what we know about capillary tubes is if you look at the velocity distribution across that pipe, it looks like this, right? It's 0 at the edges where it's attached to the glass wall of the capillary tube, and it's a maximum in the middle. We can get an expression for it. And so if you start a particle of TCE at the edge of the pipe versus one at the middle of the pipe, you know that when you've gone down a certain length in the pipe, the distribution of concentrations actually will look just like this velocity field, right? This one won't have traveled at all, and the one in the middle will. And so they're all mechanisms, if you think, of being able to take an original uniform distribution of this concentration, which would be uniform at the starting block at the upstream part, and if you look sometime later, it would be distributed along the pipe. So the one thing that all of these things have in common is that they allow stuff to spread out as it goes downstream, and you see that all of these go from looking like a uniform distribution this way at a point, this way across a stream tube or a capillary, so that when you get downstream it looks like it's all spread out like this Gaussian distribution. And so that is mechanical dispersion in the system. It looks like this as you go downstream, and the effects of this would be in going from, well, actually it's not a bad explanation, right? In going from looking like this distribution upstream, where if you take a point in the middle of this, then it's at unit concentration, that if you look at some point partway downstream here, then it's at some distributed concentration, and if you look at somewhere where it hasn't yet arrived, I guess this would be absolutely dead flat, which is this point here. And so if you think about this, this is really, these three cameos are representing points A, B, and C as you go along here. That's all. But the important thing is it's not diffusion. It's being done by this mechanical mixing, and it's just a curiosity or a coincidence that these effects as you go downstream look like diffusion. And so what's done is to define a term which allows you to look at solving this equation. Don't really care if we write this down, but just let me write it down as d and this term is an effective mechanical dispersion coefficient. Mechanical dispersion coefficient. And so we know a few things about it. I guess we know, since the units of this when we talked about diffusion were meters squared per second, we know that this term must have the same units to be dimensionally homogeneous for this expression. And so it turns out that we can represent this behavior by a coefficient which is divided into two parts. And the two parts are a coefficient of longitudinal dispersion. So in other words, we can represent this term dl as being the product of two other terms. A coefficient which we define as a function of an aquifer, and a coefficient that we define as a function of the advective velocity in the longitudinal direction. And so just like permeability is a property that describes our aquifer, this coefficient of longitudinal dispersion is a coefficient that describes our aquifer. You have aquifer A, it has a value of this of some magnitude, some length, has to be a length, because we know that this for sure has units of meters per second. For this to have units of meters squared per second, then this has to have units of length. And so this has to have units of length, and it turns out that, so this would be a measure, if you like, of the magnitude of how dispersive your aquifer is. If it's a very small number, then it doesn't spread out much. If it's a very big number, then it does. And so we can define this behavior that represents this behavior. So we can define a coefficient that represents this behavior. If we look in plan view, yeah, okay, that's good. If we look in plan view at what we think would happen with a plume, and so if you look in map view, if you have a site that exists here, and at that site you all of a sudden have a spill that you're looking down on. And if you look at what the plume that would come out of this would look like at time t1 or t2 or t3, just as we've done before, right? Then you can imagine that if you looked along the length of this in the longitudinal direction, and you looked at plotting concentration, and you took, say, this second one, so let's look at it at time t2, then the concentration would look something like this. The front has got to some location, I didn't draw this very well, and it changes from being very highly concentrated upstream of this front to being very low concentrations downstream of the front. Actually no different from what we just kind of talked about here, this behavior here. If you look at going across this plume, then you'd expect if you drew a section across here, then that section would look something like this at time t2. Concentration, I guess this would be the y direction. And so it seems that when we write this equation that represents the behavior of what's going downstream, the actual diffusion, advection-diffusion equation we should write should be something like this. It should be the capacitance term. It should be the term that represents dispersion in the longitudinal way. If this is the x direction, plus a term, I'm just pulling this out of a hat, we haven't derived it, but take it on trust, it'll just be easier. We have a term that represents the transverse behavior. This is the y direction. And we have a term that represents the advection in the system. Advection only occurs in the, so we're drawing our coordinate system with the x direction defined exactly in the direction that the main groundwater flow is. Just like, I guess, actually question number 2 of the assignment that you didn't have to do or didn't do. So I guess it's moot. So this is our new expression. And so the magnitudes of these dispersion terms, one represents the spreading in the longitudinal direction, which is this. One represents the spreading in the transverse direction, which is this. And they're both given by the same formats. It's a material property that defines the behavior of the aquifer, the advective velocity in the aquifer, and this represents the mechanical effect that we talked about. And if we wanted to, we could include also the chemical diffusion part by just adding another term onto it that represents this. So what we're trying to do is represent both of these processes, both the diffusive spreading and the mechanical spreading, by putting them into an expression that includes both parts. This carries the plug flow downstream. These two parts allow longitudinal spreading by both mechanical mixing and also by getting rid of the concentration gradient by Brownian motion. And this one allows its lateral spreading by allowing mechanical mixing as it goes downstream and also the chemical mixing. And so those are properties that we'd like to be able to define. If we can define each of these, then we can very easily calculate what a plume looks like as we go downstream. I suppose the one remaining thing that we should mention is that this advective velocity is the advective velocity in the direction of the maximum flow. And this is the same advective velocity in the x direction that we're looking at here. So this is in the x direction, and this is in the x direction. This is not in the y direction. And the reason it's not in the y direction because the advective velocity in the y direction is 0. Right? If the main flow is in this direction, the maximum flow is this direction, orthogonal to that, there has to be 0 flow because there's no head gradient in this direction because it's orthogonal to it, and therefore it has to be 0. Okay? And so the utility of this expression is that it covers all of the cases that we could ever wish to be able to represent. And the two end-member behaviors would be very low permeability materials, so K goes to 0, and therefore the velocity goes to 0 through Darcy's law. No matter what pressure gradient you apply to it, if the permeability is 0, then the velocity is 0. The mechanical effect is 0, and the only transport mechanism you have working for you is diffusion. And it will look like diffusion. So if you look along the length of a tube, then physically what it would look like after some time is it would look like, it couldn't look like plug flow, right? It would look like this. And actually, it would, don't worry about it for now. Look close enough. That's good enough for now. Maybe a mistruth at some level. Don't worry about it. The other is the opposite end of the spectrum. So I guess the opposite would be when permeabilities are large. If permeabilities are large, then these terms are big. These terms don't change. These are often of the order, we said before, 10 to the minus 9 meters squared per second. These terms might be meters, tens of meters, hundreds of meters, and so if you have a moderate size of a velocity in here, then these terms can be larger so that they swamp these ones, in which case the flow will be dominated completely by mechanical mixing. And we can use the same expression to represent this. And so all of these expressions do is they basically use these the parameter of the velocity to weight how important mechanical mixing is in the case. In the case of clays, the velocity is very small, and this first term for mechanical mixing is completely absent, and diffusion controls the behavior, and its magnitude controls the rate of spreading. In the case where velocities are high because permeabilities are high, then this term becomes big. This term doesn't change, it's still there, but it's so trivial compared to now the large magnitude of this that the diffusional effect is trivial, it doesn't affect it. And so we can think about using that in some way. Okay? 5 minutes left, so I will make this point. So how do we look at this? So what we could do is we could do some experiments that basically represent this behavior and try and characterize what this dispersion coefficient is. And I suppose we could try writing this as being, no, actually we could do it mathematically if you want to. So this is the expression that we've just defined. This is diffusion, this is advection. What happens if we do an experiment whereby we take a bead pack, we put flow through here at some advective velocity, we put some concentration upstream, and we look at what the profile of concentration looks like along the length of it, which isn't very easy to do. But what is much easier to do is us look at the concentration at the arrival as a function of time. So this represents a snapshot at time t. If we wait for the stuff to come out of the end, we'd end up with a residence time distribution which looks like this, right? This plug flow. This would be for dispersion equals 0. This would be for dispersion greater than 0, right? And so this would be dispersion 0. this would be dispersion greater than 0. So this is a snapshot. If you take a picture of the aquifer, if you could, can't really do that very well in an experiment. This would be how we measure it, by looking at what comes out the other end and seeing how that changes as a function of time to be able to plot this residence time distribution. If we have this residence time distribution, we should be able to calculate, although we haven't said how, what this dispersion magnitude would be. Right? So that's the experiment. And so what we could do is we could flow this at very small advective velocities, and we could flow it at very high advective velocities and measure to see if this dispersion changes. And what we could do is we could plot it by dividing this through by d star. So this is a diffusion coefficient. It's always the same. You've seen immediately that we've made this equal to 1. And so if we look at very slow flow velocities, then we'd expect that this dispersion to be only due to the diffusion coefficient. In other words, if we plot this value here that we've just done here, it'd be equal to 1. It should be here. And so if we increase the velocity, so this is high velocity, this is low velocity, it's a log scale. If we do it up to some threshold, then we still get it's only dominated by diffusion. However, once we get to some magnitude where the velocity is large enough that all of a sudden this term kicks in, then I suppose we'd expect this would be just a linear function of velocity. This is a log scale, this is a log scale. So I suppose actually we'd expect at some stage it to go up here, and this would be 1 log cycle to 1 log cycle, right? This should be proportional to the velocity. This is a function of velocity. And so all this expression is doing is it's measuring the dispersion coefficient that you get from a bunch of experiments by running them at different velocities and plotting them, which are these dots that we have here. And then it's trying to rationalize exactly why they look like this. And the reason they look like this is that at some very low velocity region, it's only diffusion that's occurring because this term is large compared to this, and it's that effect that we see. At very high velocities, it's only dispersion occurring, this kind of mechanical mixing that goes through. It looks like diffusion, but the mechanism is absolutely not diffusion. And it gives this behavior here. And somewhere between those 2 points, there's the transition where it's not completely overpowered by here on the right-hand side and not completely dominated by here on the left-hand side, but they're of some kind of equal importance. And so that's all this figure is. So these would be gravels and maybe fractured rocks. And these would be clays. These diffusion coefficients in an absolute sense would be close to molecular diffusion coefficients, which we've said are very low, maybe 10 to the minus 9 meters squared a second. And so it's no surprise that if you want to build a landfill, you either line it with clay or you build it in clay, because all of a sudden the rates of diffusion, not only the rates of permeability are low, making this velocity here very low, the only transport mechanism you have is by molecular diffusion. And so clays, the transport process is completely dominated by diffusion. It's always a very low number, and therefore that's why you put nuclear repositories in low permeability rocks, because this term, dispersive term, is 0, and you only have to worry about diffusive transport. Likewise in landfills. If you looked at, instead of looking at the behavior along this sample, but if you had a very wide sample, or if you looked at, a much better explanation, if you looked at the plan view of a plume, and you looked at this lateral spreading, which is this distribution, and use this expression and measure the transverse dispersion, then you end up with basically the same result. One to one, a mixed region where diffusion and dispersion, mechanical dispersion, are important, a place where mechanical dispersion dominates, and a place where diffusion dominates. So that's it. So PDEs, I guess, are useful for us to be able to understand and quantify exactly what's going on. It's important to understand what the PDEs are in terms of what they mean. This is diffusion-like behavior spreading things. This is behavior that advects things downstream, the plug flow part. And this is the accumulation term. All told, they allow us to say something about rates at which plumes develop. And if we understand something about the appropriate coefficients which go in here, then we can use these things judiciously to say something about how our system works. And the only important thing to remember about these coefficients are to remember that part of it represents a mechanical mixing, part of it represents a diffusive mixing. They're very different mechanisms in very different materials, but they look the same. And so that's the reason that they can both be used in the same expression. So I'll leave it there. Great. Thanks.